everyone. So the last talk is by Shu Liu, Haodong Sun, and Hongyuan Zha, and its title is A Particle Evolving Method for Approximating the Optimal Transport Plan.
Okay, so we are very happy to get the chance to present our work at the GSI conference. So the title of our presentation is Approximating the Optimal Transport Plan via Particle Evolving Method. My name is Shu, and I will present the first part. Later, one of my collaborators, Haodong, will present the second part. So we decide to divide our presentation into different sections. We will first start with the background. So the classical optimal transport problem is first discovered by the French mathematician Monge in 1781, and is formulated as this constraint optimization problem. So we are minimizing over the transport map T, satisfying T push forward distribution mu equal to nu, and we are minimizing the cost, the average cost function. So this image illustrates a real-life application of the OT problem. So, for example, we have a pile of sand and we have some holes here. What is the minimum cost of moving this pile of sand to filling these holes? That is a typical classical. That's a typical OT problem. However, the classical OT problem is not it's not applicable everywhere. For example, if mu is a point distribution and the nu is a Gaussian distribution, in this case, there is no map T such that T push forward mu equal to nu, right? So in order to compensate this, we come up with the generalized OT problem. The generalized version of the OT problem, which is called the control-ish problem. So in this case, we are minimizing. So instead of minimizing over the transport map, we are minimizing over the joint distribution. So we are minimizing the joint distribution gamma with fixed marginals equal to mu and nu, and we are going to minimize this average cost. And we will denote the optimal solution for the control-ish problem as gamma OT. We call it the optimal plan, optimal transport plan. And these two figures are two examples of the optimal transport plan. So this one shows the black dots shows the optimal transport plan for a discrete OT problem. And in this figure, the black curve shows the optimal transport plan for a continuous OT problem. So that are basically the backgrounds of the OT problem. And now I want to say something about our goal. So our research is motivated by these three aspects. The first one is because the OT problems themselves are important, and second is that there are not many methods that can deal with the OT problem with known marginal densities on continuous space. And the third aspect is that we are interested in the samples. The samples are important because the important statistical information of the optimal transport plan can be efficiently retrieved if we can generate samples from the optimal OT plan. And our research goal is as follows. Given the probability distribution mu and nu, we want to propose a method that can generate samples to approximate the optimal transport plan gamma OT. Okay, so to illustrate our algorithm, our method, we should start with the relaxed version of the control-ish problem. So to introduce the relaxed version, let us first recall the control-ish problem 1. And we can prove that the problem 1 is equivalent with this minimization problem without constraints. As a trade-off, we need to add 2 regularization terms after the average cost. And these 2 regularization terms contains the regularization function iota. The function iota is a strict regularization function. It equals to 0 when input is 1 and is positive infinity otherwise. And you can easily check that this minimization problem is equivalent with the control-ish problem. Okay, and our idea is that since the regularization function iota is not a regular function, if we what about replacing it by a smooth function f? So in our research, we set capital Fs equals to S log S minus S plus 1. And if we replace the iota function by this f, we can check that the previous regularization terms here, it will reduce to the KL divergence term. And as a result, we are going to minimize this relaxed functional. So we call it epsilon lambda KL. KL stands for the KL divergence, and lambda stands for the coefficients ahead of this KL divergence. And for this kind of relaxed problem, we have the following consistent theorem. So the theorem basically says that if we consider the quadratic cost, and we assume that mu and nu are belong to probability distributions with finite second order momentum, and they have densities, and they all satisfy log Sobolev inequality with two constants. And we assume that the coefficients lambda n are an increasing positive sequence, and this lambda n approaches to positive infinity. So under these assumptions, we can prove that the sequence of the functionals will gamma converges to the epsilon alpha functional, which is associated to the control-rich problem. And the corollary in the red text are the main result of the theorem. So it is said that the functional epsilon KL will admit a unique optimal solution gamma n. And the original OT problem also admits a unique optimal solution gamma OT. And we can prove that gamma n will converge to gamma OT in the weak sense in the probability space. So basically speaking, this theorem justifies the consistency between the relaxed and the original problem in the asymptotic sense. And if you are interested in the proof of this theorem, you can check the archive preprint here. Okay. So after we have verified the consistency of our relaxed problem, our goal is just minimizing our relaxed functional. So the most natural idea is to apply gradient descent algorithm. And as a result, we are applying gradient descent on the probability manifold. Since it's a manifold and we are applying gradient descent, what kind of metric should we choose on this manifold? So our answer is the 2-Wasserstein metric. So the reason is that the corresponding, so if we choose 2-Wasserstein metric, the corresponding manifold gradient flow, it can be realized by evolving a particle system, and thus is more tractable to implement and easy to be extended to a higher dimensional case. Okay, so now let us just write down the 2-Wasserstein gradient flow of the functional. It is the equation 5. And if we denote the density of gamma t, the distribution gamma t as rho, and similarly rho 1, rho 2 are the densities of marginal distribution mu and nu, then the equation 5 can be written as a time-evolving partial differential equation of the function rho. Here, rho 1 and rho 2 are just the marginals of rho. And the details of the derivation of this PDE can also be found in the archive preprint. Okay, and so if we focus on this time-evolving PDE, you can treat it as a continuity equation, and you can tell that this gradient part can be treated as the driving vector field of the particles, and that will motivate the following particle systems. And this particle systems contains two components, xt and yt. And here, rho 1 and rho 2 are the densities of xt and yt. Okay, so now after a large enough evolving time t, we get a large bunch of particles xt and yt. So let's stop here and take a look at the big picture. So why this large bunch of particles xt and yt can approximate the optimal transport plane? It is that it can be explained as follows. So this large bunch of particles, they can be treated as the samples from gamma t, and since t is large enough, evolving large enough, this gamma t can be treated as a valid approximation of the minimizer of the functional epsilon. And since we have proven the consistency theorem, when lambda is large enough, this gamma lambda as the minimizer of the epsilon functional can be treated as the valid approximation of the optimal transport plane gamma OT. So as a result, our large the large number of particles xt yt can be treated as approximation of the optimal transport plane. So now I'm going to invite Haodong to introduce the details of our algorithm and show you some numerical examples.
Yeah, thank you, Shu. Now let's take a closer look at the algorithm design part. So for equation 7 on the right-hand side, we can see we have a grading log rho term. So since for each iteration, we only have the particles, so the closed form of the density corresponding to the underlying distribution is not available. So the grading log rho here is not tractable. It's not tractable. So to remedy this issue, we want to find the approximation of this term. So here we just use the globing method. For more details of this method, please go to reference 9 for more details. So the general idea is as following. So for the grading log rho term, by globing method, we just replace it by its convolution with the modifier. So here the modifier is chosen to be this RBF kernel. And by doing this convolution and also applying some simple integrate by parts, we can rewrite this term as this fractions. Actually, both the numerator and both the denominator and the numerator can be represented as expectation. And assume that now we have m particles as samples from the distribution rho. Then this expectations can be simply written as the finite sum as another approximation. So now we obtain a tractable form for the grading log rho term. So this is the first computational trick we apply here. And we also apply the random batch methods here. And for more details, please go to reference 10. For this grading log rho term, we need to evaluate this term for each particle. And as our approximated term shows, for each particle, you need to invite these two finite sums. So for each iteration, each particle, the computational cost is of the order n. And since total we have n particles, so the total cost is of the order n squared. But actually, to get a nice approximation of this term, we don't need all the particles. We can apply this random batch methods by simply dissecting the total number of the particles into m batches. And then for particle in each batch, to evaluate the grading log rho, we don't need to use all the n here. We just need to use all the particles in the same batch as that particle. So by doing this, we're able to reduce the computational cost from O(n) squared to O(n) squared divided by m. So we just need to choose this m properly and based on our experience. And this slide just give a summary of the particle system equations here. So this term grading log rho is already replaced by the kernel density estimation. So that's given by the globing methods. And the next slide just give more details and a summary of our algorithm. So the input includes the marginals, time step, and also the total number of iterations and the parameters of the given RBF kernel. And we initialize the locations of all particles according to some simple distributions. And then we start to run our algorithm. So for each iteration, first we shuffle all the particles and divide them into m batches. And then for the particles in each batch, we update the location based on the particle involving equations we have before. And we don't need to use all the particle to evaluate the approximation of grading log rho term. We just need to use the particles in the same batch. So that's how we reduce the computational cost. And finally, after long run, we're supposed to have a nice sample approximation of the optimal plane. We also find that our framework can be easily generated to multi-marginal optimal transport problem. As one example, we have this one-step barycenter problem here. So finally, let's show some results for the numerical part. So the first experiment, we start with one simple Gaussian case. The red and black dashed lines correspond to two marginal distributions we give here. And the solid blue and green lines are the marginals of the kernel estimated density of these particles. So finally, after some iterations, this marginals estimated from the particles should coincide with the given marginals, and we do observe that. So the first one just shows the correctness of our marginals computation, and the second one just shows the optimal, just shows the samples given to represent the optimal coupling. So we start with some initialization, and then after 1,000 rounds, we're able to have this nice optimal plan, and it's all the particles concentrated around this orange line, which is actually corresponds to the optimal transport map. So according to our setting, the optimal map is just given by this linear map. So the particle just concentrate around this orange line. And for the second experiment, we try a little more complicated case, 1D Gaussian mixture. The green and so the red and black line again gives the marginal distributions, and the histogram indicates the distribution of the particles after 5,000 iterations. So you can see the marginals here are very close to the given one. And we also have the right-hand side, this graph represents the sample approximation for our optimal plan. The third experiment, instead of doing 1D, we're doing a 2D experiment. So let's say we have two grayscale image. So for example, we have this star and two disks, and some similar case will be like handwritten digits. The marginals are given by number 6 and number 1. For this grayscale image, we can interpret them as distributions. So we just represent this grayscale image by a lot of Gaussian. So we make a weighted sum. So the each Gaussian distribution will be centered at this point, and finally we make a weighted sum. So this will be our given marginals. And by applying this algorithm, we're able to have the optimal coupling. So since we're only considering W2 distance here, so we can easily obtain a constant speed geodesics from that optimal coupling. So we have approximated geodesics. So this graph in between just gives some samples from this geodesics. So you can see we can have some interesting and nice results here. And for the final experiment, we consider the extension of our framework, which is Western barycenter problem. So still a 1D Gaussian case. So the red dashed line corresponds to two marginal distributions we give here. So these two are just two symmetric Gaussian. So they center at positive 10 and negative 10, and they have the same covariance. They have the same standard deviation. And then by applying the algorithm, we're able to have we are able to compute the optimal, we're able to compute the solution to this Western barycenter problem. So if we tune the weight to be equal, then the marginal of the zero axis marginal should just converge to the distributions in between, which is centered at 0 with the same standard deviation. And if we make the W1 smaller, then the convergent distribution should be closer to the right distribution and centered at 5. And if we just change the order, we make the W1 larger, then this convergent distribution this marginal should be closer to the marginal on the left-hand side. Yeah, so this just numerically verify our Western barycenter formula. And finally, let's mention one important related work and also some future work. So recently, we learned from arXiv there's one work which shares very similar idea with us, but done by another group of researchers independently after the submission of our paper. So we just want to mention this work. And for the future work, we just want to do the future work from 3 perspectives. So for the first one, we want to further establish more quantitative study on how well the original optimal OT plan can be approximated by solving our minimization of the functional. And we also want to study on the displacement convexity of this functional. So we give some simple results about the convexity, but displacement convexity will be more interesting. And finally, we will work on more numerical examples, especially considering some higher dimensional case. Maybe probably include the neural network. Yeah, so that's all about our work. Thank you very much for the time and attention, and all the related questions are welcomed.
Okay, thank you very much, Shu and Haodong. You guys are here, if I am correct. So I have just a very quick question to kind of close the session. So how different it would be the energy that you consider, I mean, couldn't the energy just be the sinkhorn energy and, just basically do the gradient flow of that energy in their usual sense? I mean, am I interpreting things correctly? So you're really taking the sinkhorn type energy and then doing the gradient flow for that energy?
Oh, so you are saying the sinkhorn, so maybe just add adding the entropy term after the expectation of the cost function. Yeah, so actually our scheme is kind of different from sinkhorn, because if you do sinkhorn, you still have the strict marginal constraint. But in our case, by adding the two divergence function, we are just eliminating the strict constraints. So it becomes a pure optimization problem instead of an optimization problem with constraints.
Okay. Okay, sounds good. Okay, so that was my quick question. So yeah, thank you guys for your talk. And so, okay, this is the end of this session, and but don't go just yet. So Frederick is going to give closing remarks for the whole conference. So just stay around in this channel. So for now, thank you all, and let's just wait for Frederick.